Good evening, everyone. Today we will be discussing the fermentation industry as a part of organic chemical technology. Let us start with our today's topic, fermentation industry. Starting with the introduction of the fermentation industry, you like to know that what is the fermentation process. So the chemistry concerned with the fermentation process is known as gymology. In fermentation process, what happens? A larger molecules that will be converted into smaller and very simpler molecules. So in the overall fermentation process, what happens? We know that in the fermentation processes, there are involvement of the microorganisms. The microorganisms can be bacteria, yeast, molds. So that their difference will be discussed in the next slide. So these kind of microorganisms, they grow in a nutrient media by uh, maintaining a physiochemical conditions, and thereby they convert the feed into our desired product. So there will be in the whole fermentation process, there will be microorganism, as well as for their growth there will be one nutrient media, and there will be some physiochemical changes in the overall process, and some conditions at a certain conditions like pressure, temperature, pH, and many other critical factors are there. In the presence of those critical factors correctly maintained and in a controlled way, so there at the end we will get the feed to be converted into our desired product and with the estimated yield. So for getting the yield, we need to have control over the critical parameters for a fermentation process. Fermentation technology is the use of organisms to produce various foods, pharmaceuticals product, alcoholic beverages on a large scale. So fermentation technology is very much into practice for a large scale application in the food industry as well as um, pharmaceutical products. The necessary requirements for fermentation to occur is the presence of carbon, nitrogen, salts, trace elements, and also the vitamins. These all are needed in the nutrient media, as well as the extra addition of trace elements and vitamins are needed for the growth of the microorganisms in the nutrient media. The end products formed as a result of the metabolism of the microorganisms during their whole lifespan, they are released into the media. Due to the metabolism occurring inside the microorganism for the certain period of time of fermentation, we will be getting end product that is in the nutrient media. They will be releasing the end product into the media, which is extracted further, and they have that extracted product of the fermentation have very high commercial value. So we will like to see that what are the major fermentation products we get. Suppose we are targeting some industrial chemicals. So industrial chemicals, largely there is production of ethanol, for which the organism used or microorganism used is Saccharomyces cerevisiae. Lactic acid is also produced in large scale, that is Lactobacillus bulgaricus. So these are some microorganisms which are involved for the production, fermentation production of ethanol. Similarly, when you are targeting to produce enzyme like alpha amylase there will be involvement of the microorganism like Bacillus subtilis, then Protease, then Bacillus species, Lipase, Saccharomyces, Lipotica. In the category of antibiotic, there is huge production of the penicillin. Penicillin for that the microorganism used is Penicillium chrysogenum, Streptomyces griseus, and so on. Vitamin, one example I can give, riboflavin. There, these microorganisms are involved. Vitamin B12, these microorganisms. So you need to you need to focus on the pattern that every um, for every um, production of any fermented product is very specific to the selected microorganisms. You cannot get ethanol by applying the by introducing the microorganism in the nutrient media lactobacillus. This microorganism will not help you to get convert into the product. Like it also depends on the variation of the raw materials, variation in the changing in the conditions of fermentation, and also the change in the microorganism. Your product will be different. So it is very specific production of the product for some specific condition. Okay. So we were talking about microorganism. So yeast and bacteria are unicellular and they have very small dimensions. Yeast are irregularly oval in shape and they have diameter of 0.004 to 0.01 millimeter in diameter. And you notice that yeast they multiply by budding method. Okay. Whereas bacteria, they are very smaller, mostly less than 0.007 millimeter, okay, less than the highest, less than yeast, you can say the size, in the longer dimension, and they are more diverse in the shape. There is no certain shape, but overall the length can be mostly less than 0.007, but the shape is very, like it may vary. Bacteria, they multiply by the binary diffusion method. Now, these kind of division methods of the microorganisms, these are very um, broad area in the biotechnology field. So, I am not discussing in details those part. Uh, Now, later on, the molds, they are multicellular filaments and they increase by vegetative growth of filaments. This method they follow. So, every microorganism has their own method of one different method of multiplying their cells. Okay, these microorganisms, molds, they employed in the fermentation require very specific environments and very specific foods to ensure their activity. Okay, so their activity depends on many factors. We will discuss the concentration of the sugar or the substrate you are putting into the nutrient media, that will affect the product. If you change, if there is concentration, if it is very high concentration, then product quality or yield may be different. And there is, if there is very high contamination of the raw material, then that may also cause in the poor quality of fermentation, or it may happen that in the middle of the process the fermentation may stop because their growth cycle will stop. Microorganism growth cycle may stop. So the most favorable temperature is a very important Temperature is a very important factor for fermentation process. It generally maintains at a ambient temperature like 5 to 40. So it generally maintain less than 40 degrees Celsius is very uh, good for maintaining the fermentation. Some microorganisms they require air in the presence of air. They need to do the metabolism in presence of air. So those are classified as aerobic bacteria or aerobic microorganism, and others they go through their life process without the presence of air. They are called anaerobic bacteria. Okay. So during the microorganism growth period, in addition to the food or energy resources, there should be various nutrients are to be supplied from outside, just like phosphates, nitrogen compound in an adequate quantity to to boost their growth phase. Okay. Now, uh, this is the thing that basic prerequisite of a good fermentation process. So a microorganism that forms a desired end product. We need a microorganism. There should be a selected microorganism to get a desired end product. Okay. Now this organism must be readily propagated and be capable of maintaining biological uniformity, thereby giving a predictable yield. Okay. Economical raw materials for the substrate, just like it can be starch or any other level of like any other sugar source like sucrose, any other form. So there should be, for a good fermentation, we can categorize it as a good fermentation occur. So there should be estimated or acceptable yield. There should be rapid fermentation, a product that is readily recovered and purified. This step is very important. Okay, how you are recovering or filtering the thing and purifying your ultimate product, that is very important process in a fermentation. At least fermentation, there is a very important step for recovery of the product and its purification. So next is some chemical conversion in the fermentation process. So fermentation process, we give a substrate or the raw material, that is a sugar in the form, and they undergo various chemical processes. First, we will discuss the oxidation process. Oxidation process occurs, and some of the examples are alcohol is converted into acetic acid, sucrose is converted into citric acid, dextrose is converted into gluconic acid. So this kind of conversion is occurring during the fermentation under some controlled condition. We will be getting this acetic acid, citric acid, gluconic acid as an end product by this oxidation chemical process. Okay. Similarly, when it is a reduction chemical process, then aldehydes will be converted to alcohols, sulfur will be converted to hydrogen sulfide. Okay. Hydrolysis chemical process, in which starch is converted to glucose and sucrose is converted to glucose fructose and other alcohol. Esterification reaction, it is also may occur during fermentation, where the hexose phosphate from the hexose and phosphoric acid is being produced. Okay. Now we will briefly discuss about the components of the fermentation process. Component means, suppose you are going to start a fermentation process. So what are the things you need to have the source of before starting your fermentation process? So there should be some procedure, and there should be certain requirements to proceed with your fermentation process to get your ultimate desired product. First is medium formulation. Medium means in which they are in which the microorganism growth will be occurring, and due to their metabolic activity, there will be production of, or there will be certain chemical changes, and there will be conversion of raw material to our desired end product, fermented product. Okay, so medium formulation, the growth medium provides essential nutrients. They provide essential nutrients for the microorganism to grow, okay, and to produce the desired end product. A typical fermentation medium contains carbon sources. Why carbon sources needed? They provide the energy and these carbon atoms for the cell growth and product synthesis. They provide the energy. Okay. Example like when you are introducing glucose, so there will be carbon, sucrose, fructose, molasses, starch, which they are the raw material for converting them into a fermented product. This may be as a source of carbon. These are when the nitrogen source is also required. These are required for protein synthesis of the microorganism, because they need to grow and multiply in cells so that um, they grow from single cell to multiple cells. Okay, and the fermentation process carried on. So they are required for the protein synthesis and cellular components. Common sources of this nitrogen in the nutrient medium, that is the ammonium salts that we generally add extra in the nutrient medium, yeast extract, peptone, or soybean meal. Various, it depends on the process and the raw material and the desired end product. So this kind of variation of the nitrogen sources we generally use in the fermentation medium. Phosphate salts, these are essential for nucleic acid synthesis and energy metabolism. So there should be addition of mineral salts. So mineral salts, they are like trace elements like magnesium, potassium, calcium, sulfur, and these are necessary for the microbial growth overall. Vitamins and other growth factors are also needed. This may be added to supplement the medium, especially when using fastidious microorganism. Buffer buffer is also added in the medium to maintain the pH of the medium within the optimal range for the microbial growth and the end product formation. So you need to take care that medium optimization is a very critical step to ensure the maximum product yield and the quality. Medium optimization should be there. You are suppose you are starting with your medium formulation for the fermentation process. Now you have the idea of that these kind of things you need to add to get the to get a desired product from this raw material using this microorganism. You know all the things, but during your experiment or during your process starting, there will be some changes in some parameters. The little bit change, like you are suppose I'm talking about pH. If the pH is not neutral, if it is so much acidic, if it is so much basic somehow due to the addition of your some product, then if you are not maintaining the pH in a proper way, there will not be occurring the growth of the microorganism in a certain way, or maybe there will be death phase. Okay, now the growth curve and this kind of microbial growth we'll be discussing later. So uh, any other example, like in the experiment or in the medium formulation, if you are not maintaining the temperature, if the suddenly somehow the temperature becomes more becomes like exceeding the ambient temperature, it becomes 50 or 60 due to the exothermic reaction occurring in the medium. uh, in various other various examples or in the cases. So if the temperature crosses, then there will be again a hindrance in the microbial growth. So the overall fermentation process will be affected. So you need to start with your experiment in a such a way so there will be more trial and errors, and you need to get the optimized value for all the parameters, that this much for this much of yield of product I need to add this much of carbon source, this much of nitrogen, pH should be maintained in this value. Temperature should be in this range only. It should not cross much, and it should not drop much. So this kind of parameter optimization is very required for overall formulation of good medium, or getting the maximum product yield and quality. So factors to consider include the concentration of the nutrients, as I already discussed, concentration of the nutrients, pH, temperature and aeration. Means you are passing the air or it is happening in absence of air. Suppose you are doing experiment and you don't know that somehow there is leakage in the leakage, or there is some escape of air, some condition occurs that in the anaerobic fermentation process the air is also somehow it is getting into the reactor. So obviously your desired yield will be not you will be not having. Also it may be possible that the end product is different, or there will be some contamination, or there will be some other difficulties. So you need to ensure that all the critical parameters, because it is a microbial growth, okay, and all depends on the microbial growth. So these kind of factors are very critical to maintain the optimization environment for the maximum product yield. Okay, next is the microorganism. So the next component for fermentation is microorganism. The choice of the microorganism is very crucial for the success of the fermentation process, and the factors include product specificity. Now the microorganism must be capable of producing that particular desired product. Okay, now the growth rate, the microorganism should have high growth rate to maximize the productivity of our desired product. Product yield, microorganism should produce the desired product at a very high yield. There should be high yield. Obviously, we will select the microorganism in such a way that they should be capable of giving you the maximum yield of the desired product as minimum matlab, as minimum period of time that is expected. So we will be choosing and selecting microorganism in such way. Product yield, the microorganism should produce the desired product in a high yield. Metabolic stability, microorganism should be genetically stable, and that should be resistant to the mutation. There should not be mutation occurring during that period. So strain improvement techniques such as genetic engineering can be also used to enhance the performance of the microorganism for specific fermentation process. Fermentation process involves cultivating of the microorganism in a bioreactor under controlled conditions. Key factors are temperature, obviously pressure also is important, temperature, pH, aeration condition and agitation. Temperature, some optimal temperature like less than 40 degrees Celsius or 35 to 40 degrees Celsius is maintained for microbial growth, and the product formation varies depending on the microorganism. The pH of the media must be maintained within the optimal range for microbial growth and the product synthesis. Aeration, adequate aeration is essential for microbial growth, and the supply of oxygen, obviously it is needed. Adequate quantity of oxygen supply is needed for if you are using or if you are handling the aerobic process. Agitation, why agitation is very required, that is I will discuss. Agitation also help to ensure the uniform distribution of the nutrients and oxygen throughout the fermentation process in the fermentation broth. Next, the last step is the downstream processing. That is the purification and extraction and purification of the of your desired product. Now, the downstream process involves the separation and purification of the desired product from the fermentation broth. Now, the common techniques involve filtration. This used to remove the cells and unwanted particulate matter to be separated from the broth. Solid separation, solid liquid separation. Centrifugation, this is used to separate the product from the broth based on the density. Chromatography, this is a powerful technique for purifying the products based on the size, charge, affinity. Crystallization, obviously it is used to purify the solid products in the form of crystals. Also the drying to remove the extra moisture from the purified product. Now the specific downstream processing steps will depend on the nature of product you are getting. According to your uh, desire, it will be we will modify those kind of steps in the downstream processes. Okay. Now, see, this is the bacterial growth curve. You need to understand that why I am very much in giving importance on the presence of these critical factors, because these critical factors, if there is any change in the critical factors, this whole lot of this growth curve, you can see this whole lot of growth curve, this time and this thing will completely change. So you need to do certain trial and error methods to get the optimum conditions to maintain over the like in a certain way, so that you are getting maximum yield of the desired product every time. So these kind of parameters uh, you need to select and choose to and for the optimization process. Now see, this is the bacterial growth curve. This is the in the logarithmic scale it is plotted, and x-axis is the hours time. First is the lag phase. Lag phase is there is no growth of the microorganism cells. There is no growth. They are not multiplying. These are only keeping like getting bigger in the size, but the cells are not multiplying. So this is kind of stationary phase, you can see, and at the end of this there is certain increase in the number of microbes cells. So there will be cell division, rapid cell division will be there, and there will be exponential or logarithmic way. There will be a certain increase in the curve in the phase. There will be, after that there will be saturation. Saturation means it will not multiply, or it will there will be no cell division anymore. So there will be a stationary phase. After stationary phase there will be cell decompose any other factors, so death, the number of cells will be reducing. That is called the death phase. Okay, so some cell still will be there in the whole medium. So this is overall the bacterial growth curve. Now discussing each phase separately. First, lag phase, right? Yeah. First phase is lag phase. So in the lag phase, there is no growth. During this phase, bacteria becomes mature, but they do not divide into multiple cells. They just adapt into their environment. The cells are metabolically active, and they only continue to increase in size. They don't multiply. They only increase in size. If the cells are smaller, they become bigger. Okay. The length of the lag phase can vary depending on the difference between the new and original conditions and the condition of the bacterial cells. Second phase is the log phase. Log phase is the logarithmic or rapid exponential cell division is occurring. Bacteria experiences at this log phase, bacteria experience the maximum growth rate, and the population becomes double almost at a constant rate. The exponential phase is marked by a steep, that is upward slope on the growth curve graph. Factors such favorable environmental conditions and enough nutrients contribute to the high metabolic activity, and there is more cell divisions of bacteria during this stage. The growth rate becomes slow down of the log phase. At the end of the log phase, the growth rate slows down when there is presence of toxic substances in the medium, and they start to accumulate. Now the third phase is, we have seen the third phase is stationary phase. Stationary phase, you can say that this is the equilibrium phase. There is equilibrium bacterial growth. That means the number of new cells are created, there will be equal to the number of cells that are dying. So there is no overall population growth. Gradual depletion of the nutrients, accumulation of the waste products, and limitation of the space and crowding. So these all are occurring in the stationary phase. So these certainly gradually these push the bacteria to all the microorganisms to enter into the last stage, that is the death phase. Fourth stage is the death phase. This is the final phase of the bacterial growth. Here, the rate of the cell death exceeds the rate of the cell division in a bacteria culture. During the death phase, the number of living cells decreases exponentially. So there is again this it is the lag phase, it is the log phase, and it is the stationary phase, and then again there is exponential decrease in the value. This phase is called death phase, exponential decrease, right? So death phase can be caused lack of nutrients. If you are not giving for this much of microorganisms, if the cell division is occurring, but you have not provided the sufficient nutrients into the media, then obviously in the between they will stop multiplying. There will be lack of source of energy and other thing like carbon, nitrogen, and other thing. There will be lack of those nutrients, and due to the lack of those nutrients, they will be stopping their cell multiple mechanism, and they will automatically enter into the death phase. Now there might be some injury to the cell or environmental temperature change. So these are some factors that may cause the microbial growth to push in, like to enter into the death phase. So we have discussed in details what are the phases a microorganism generally generally goes through different phases, right? Now coming to the critical factors for fermentation. Yeah, so we were discussing about the critical factors of fermentation. Critical factor is pH. So, what is the pH is what pH should be maintained for maximum growth of the microorganism. So, pH should be maintained neutral pH for faster growth of microorganism. Right? Now the temperature is very specific to bacteria species, right? Different kind of bacteria, and obviously it has some optimal value of temperature. Optimal value of temperature for maximum growth. Aeration. Now you need to do the supply of oxygen O2 for aerobic condition, right? And there will be um, very low level or absence of oxygen when you are maintaining anaerobic fermentation process. Water, obviously water, you when I'll be discussing the flow diagram for each production, then you will see that there is lot of dilution before putting the raw material to the fermenter, and because this will help the microorganism to grow in a proper way. So sufficient water for the growth. Optimal moisture level should be maintained. Should be maintained over. Okay. Now the agitation, for what purpose we need to do? To maintain the homogeneity of the nutrients, that we are adding lot of things as a vitamin or other sources, so we need to agitate the solution. Homogeneity of the nutrients, also it promotes the rate of nutrients uptake. Also it promotes the aerobic condition. Okay, aerobic conditions and so on. Also uniformity of the temperature. Uniformity of the temperature. So these are the things are very essential. Now the pure culture fermentation. Pure culture you need to maintain to minimize the risk risks of contamination of the medium or product, and also the consistent product quality. And last is the uniformity of the yield. Okay, I hope these all things are clear to you. What are the critical factors we need to maintain? So there are fermentation techniques. There are two types of fermentation techniques. There is this is solid, okay, solid state fermentation, and another one is the submerged fermentation. So in the solid state fermentation, fermentation occurring in the absence or near absence of the free water. Whereas in the submerged fermentation, it is occurring in the liquid state. It is occurring in the liquid. Sorry, wait. In the submerged fermentation, we see that there is a liquid state in which the which contains all the nutrients. But here it is absence of any free water. Solid state fermentation, they utilizes solid substrates like bagaces or paper pulp or bran. Whereas submerged fermentation, they utilize free flowing liquid substrate like molasses or broths. Okay. Solid state fermentation substrates are utilized very slowly and need not to be replaced again. But in the submerged fermentation, substrates are utilized quite rapidly and they need to be replaced constantly. Culture media in the solid state fermentation involve three phases: solid, liquid, and gaseous as well. But in the submerged fermentation, it is involvement only the liquid and gaseous phases. Here, the inoculum is very larger always, but here inoculum ratio is very smaller. Solid state fermentation, the system may or may not involve the agitation. Maybe it is not required. But in the submerged fermentation, the agitation is very, very essential. Now, in whole of the rest of the lecture, we will be focusing on the submerged fermentation only, where there will be presence of the liquid substrate. Okay, there will be free liquid into the medium or into the system. So in the submerged fermentation process, there are some critical engineering problem that you need to take care of while process of fermentation. First one is the kinetics of the submerged aerobic fermentation. Kinetics following are primarily considered depending on the phases of contact and the reactions. Suppose this is a gas and liquid contact. By proper dispersion of the air in the tank and oxygen transfer between gas bubbles and liquid. So this kind of rate may be affected. So this kind of maintaining this kinetics of the aerobic submerged fermentation, it is an engineering problem. That what should be the uh, gas to gas and liquid contact, what should be the mass transfer between gas bubbles and liquid. Second is the liquid and solid transfer, in which the dissolved oxygen and the substrate are transferred to the solid organism. Next is the reaction of oxygen and substrate in the presence of the microorganism. So these are some kinetics are involved. Next, we can see one example like considering the gas liquid contact system. Okay. Now gas liquid. Now we are supplying aerobic condition. So we are supplying oxygen into the system. So now the question is, what should be the rate of oxygen absorption? Now here this rate of oxygen absorption is calculated by a equation into pi into this uh, driving force, where this one is mass transfer coefficient, this one is total gas pressure, and this one is uh, driving force. You can see where y is where y is the equivalent mole concentration, mole fraction concentration of oxygen based on it is a gas phase, right? So this is the rate of absorption. So here you can see this kg value. It is important. I am marking with the another color. This kg value is important. Now this kg value is plotted against the PV. PV is the mixing per unit of per unit volume. Okay, so this is related by this for a given temperature and a fixed value of this driving force in the gas phase. So we can see when the relation is this kg varies with PV to the power 1/3. This equation they follow. There will be certain increase in the mass transfer coefficient. There will be lot of rate of oxygen absorption, but after a certain point there will be decrease in the mass transfer coefficient value. So here we can point out a point when we will get the optimal value for the mixing power consumed, and for that there will be maximum value of the mass transfer coefficient. Okay. So why there is certain decrease in the mass transfer coefficient? It may be due to the rupture of the cells by vigorous mixing or agitation process that creates lot of shear stresses. So that may um, hamper the microbial cell walls and that damage the cells. So there will be decrease in the mass transfer coefficient overall. Okay. One thing, that microorganism metabolism rate, how it is defined? It is defined as K into N into equivalent mole fraction of oxygen in the liquid, where K is the specific rate constant and Y liquid is molar concentration, mole fraction of oxygen based on liquid phase, and N is the concentration of nutrient at optimum value, at optimum mass transfer. So if you plot, then you will be having, if you plot the specific rate constant and the nutrient concentration, increasing the concentration, the rate constant will increase, but at a certain point it will be stabilized. So this point is the optimum, optimum values, optimum value of the concentration. Okay. Now for the scale up is also a major engineering problem for the submerged fermentation process, aerobic fermentation process. So suppose this is your how you like to calculate the escape velocity here. Escape velocity is small v into capital V divided by AV, right? Now small v is the volume of air by volume of liquid per unit time. Capital V is the total volume of the tank, fermentation tank, and AV is the cape area for unused gas. Now AV varies this way. AV varies d square. V varies d cube. So this escape velocity, this will be in proportional to d cube by d square, that is proportional to d. So from this relation we can understand that escape velocity increases with the tank of the size. Size of the tank. This increased escape velocity causing increased and possibly unmanageable foaming unless the tank of a large diameter and very low height is used. But in such tank, the mixing may be very illy defined. If the scale-up is done on a fixed linear exit velocity basis, the oxygen supply may be insufficient in larger volume system. So therefore, the design must be compromise involving tank shape, optimized mixing of the air supply and the exit velocity. The tank H by D ratio should be 2:3. So there should be design should be a optimized value of this tank shape mixing. Optimized value of tank shape mixing air supplied and the exit or escape velocity. This H by D ratio 2 to 3 is very important. Our next topic is ethanol production. Ethyl alcohol production by fermentation process. So we have discussed a lot about microorganisms, fermentation process, critical factors, um, then growth of the microorganisms, how it occurs, and then basically we are focusing on the submerged fermentation process. So there are some critical major engineering problem that we need to take care before designing the fermenter. The based upon the H by D ratio, there we need to consider about the tank shape, size, and exit velocity. How much aeration should be there for aerobic fermentation process, and there is also concern about the kinetics of the submerged aerobic fermentation. If you kinetics, like how the effect of mixing power is affecting the rate of mass transfer. So this kind of thing we already discussed. Now we are moving forward for the production of ethyl alcohol. So we will discuss what are the unit operations that involved for production of ethyl alcohol from the molasses, as well as starch substrate by this fermentation process, and that will be further taken care of, that how it purification is done to make it absolute alcohol out of the from the industrial alcohol to our absolute alcohol, and yeah, we will discuss. Okay, now ethanol production, the possible routes are fermentation process. One is fermentation process. Okay, so there the raw materials can be used as sucrose substrate like molasses, starch as a substrate like we can use corn, also the waste sulfide substrate from the paper mills. Petroleum processing, there will be chemical reactions like catalytic hydration of the ethylene, esterification and hydrolysis of the ethylene, and oxidation of the petroleum. So now in this today's discussion, we will be focusing on these two. Okay. Yeah. Ethanol production by fermentation process. One of the most important industrial fermentation is the production of the ethanol from sugar or molasses by yeast under anaerobic condition. Molasses that are obtained from the sugar factories is the most important raw material for the alcohol production. Selected strains of the Saccharomyces cerevisiae are the most commonly used as a yeast for the alcohol production. They have very high alcohol tolerance and they are able to produce very high concentration of alcohol. Molasses, that is the raw material for this fermentation process, they contain 48 to 55% sugar. They have mainly sucrose. To prepare the fermentation medium, molasses are diluted to the sugar concentration. The concentration of sugar is 48 to 55%. It is diluted at the extent of there is concentration of sugar of 10 to 15% by adding required water. High sugar concentration that may adversely react on the yeast, and alcohol produced may inhibit by the action of the yeast, and the fermentation time will be prolonged further. So we don't require that. We require our desired product within the minimum time. So we need to dilute the raw material. We need to dilute the sugar concentration at the extent so that there will be maximum yield of the desired product. Molasses generally contain most of the nutrient substances for yeast, but we need to add ammonium sulfate phosphate to the fermentation medium to supply some deficiency of the nitrogen and phosphorus. The pH of the fermentation medium should be maintained 4 to 5 by using sulfuric acid or lactic acid. Due to this acidic pH nature, the medium usually does not get contaminated by any other source of contamination or bacteria presence. So sterilization generally it is not required, but sometimes we need to do sterilization also if there is some contamination in the raw material. So only pasteurization of the fermentation medium is practiced. So this ethanol, the properties of ethanol you need to know, because the boiling point is very important for this whole lot of discussion uh, for maintaining the purity of the system. Property that, what is that? That is the molecular weight. Molecular weight is 46.07. What is the density of it? It is around 0.791. But at a temperature of 20 degrees Celsius. What is the melting point? It's around. So, melting point, remelting is also done in the process. We will discuss in the flow diagram. Boiling point, it's around 78.3. Okay. Flash point, 21. Ignition point, toxicity, if it is more than 1000 ppm. Okay. And grades. Okay. So here grades. One grade is anhydrous. So that is 100% pure. No water is there. 95% alcohol, which is also known as industrial alcohol. And rest of the 5% is water here. And last is denatured alcohol. This is also type. Denatured means you are also having addition, some addition of mild toxic elements. This is also having industrial applications. Suppose we are providing sucrose. Sucrose as a substrate for the fermentation process, right? So how the chemical reactions will be involved? So that we will get the ultimate of ethanol from the raw material sucrose. First is the main reaction. It is the C12 H22O11. This is nothing but sucrose. This is diluted medium water in the presence of invertase. This is the catalyst, enzymatic catalyst. So we are getting by the inversion process C6H12O6. So these are inversion. We already discussed the glucose. D glucose, D fructose. So by the inversion, this will be done, and from there, by the zymase catalyst, enzymatic catalyst, in the presence of zymase catalyst, we are getting alcohol, C2H5OH plus carbon dioxide as a gas that will escape. So this process is exothermic in nature. So this process delta H is negative, 31.2 kilocalorie. So it means this is a exothermic reaction. We need to maintain the temperature for this kind of reaction so that doesn't hamper the microbial growth. But there one thing you also have to know, there is some side reactions that you cannot control, that will happen only. The side reaction is this fructose glucose, D fructose glucose, that may go C6H12O6. They also produce high molecular weight alcohols and some aldehydes. So these are aldehydes. This is also a byproduct, and these are you can say high molecular weight alcohol. This is present in the fusel oil. We will discuss what is that. So this reaction occurs in the fermentation process. This also side reaction occurs. This is the main reaction, this is the side reaction. So what are the byproducts of necessary byproducts? One is CO2 we are getting. Second one, we are getting we are getting aldehydes, and third one we are getting fusel oil, right? Okay. This is the flow diagram of sucrose fermentation to produce the ethanol. Here the molasses storage is there. From there we are diluting. At the first stage we are diluting. Also after the diluting we are putting that into the fermentation tank. Okay. So also in the it may go to the molasses sterilizer. If it has some impurity, it needs to be stable. It needs to be sterilized at first. For that, steam is passing through the reactor and it is being sterilized. So Uh, this this molasses is then fed to the yeast culture tank. There will be culture medium, and the yeast will grow, multiply, and by this process, ultimately there will be yeast storage, and they will be fed as the fermentation tank. So in the fermentation tank, we are having molasses, the raw material, yeast as a microorganism, nutrient source, and in the fermentation tank. And due to the exothermic nature I already discussed, this exothermic nature of the fermentation chemical processes, so there will be we need to maintain the temperature around 20 to 30 degree, and we need to maintain the temperature, so there should be some cooling water circulation. So the fermentation time, it takes around 30 to 70 hours. Okay. Now from the fermentation, it occurs after this much of hour, the product will be sent to the heat exchanger. Okay. This heat exchanger, and one thing I need to forget, I forgot to mention that from the fermentation tank, due to the chemical reactions, we already have seen there will be byproduct CO2. Now the CO2, this gaseous stream may have also some moisture. Moisture in the sense there will be some droplets of uh, this ethanol that is being produced in the fermentation tank. So it should be sent through the scrubber. So the scrubber, that 1 to 2% alcohol in the stream will be collected, and that is recycled back to the this diluter, continuous diluter, because we should not waste, because it already has alcohol. So we can easily use this as a water scrub diluting medium for the incoming raw material. Okay, now the whatever thing that has been produced as a product of fermentation reaction, now this alcohol and aldehyde and water, this mixture has been passed through the preheat heat exchanger, and then a second heat exchanger, and then it is fed to the beer still. The beer still, this is a distillation only. So here the concentration of that concentration it is having, mm, concentration is increased in the process of beer still, right? So concentration increased up to 50 to 60%. Now the bottom product of the beer still, that is called as slopes. It is a waste disposal or evaporator to produce the cattle feed, or can be used as a fertilizer. Now the top product is 50 to 60% of alcohol, mixture of aldehyde, and also some sort of 50 to 60% this alcohol is becoming more volatile. So it will be collected from the upper side of the beer still. Okay, then it will be passing through the condenser, pass through the aldehyde column to remove the aldehyde content of the mixture. Now from there, as at the bottom you will be collecting water, and aldehyde will be more volatile, it will be collected at the top, and the other part will be sent to the, yeah, so the other part will be sent to the rectifying column. So rectifying column, from there we can see that at the above we are getting pure aldehyde, and from here we are having 95% alcohol as a side stream. 95% alcohol. Okay, so this 95% alcohol we are getting, we cannot, by this simply process of rectifying, we cannot go beyond this purification. We cannot go 100% pure alcohol. It still has 5% water in it. We cannot go because it reached this concentration, it already reached the constant boiling mixture. It has some constant boiling point. We cannot do some more rectification of this mixture. So it is collected as 90% ethanol. Okay. Some part of this denaturant, some toxic elements are added, and this is produced denatured alcohol. Further, it can be taken as anhydrous steel, where the makeup benzene is added. Benzene for disturbing the system of the constant boiling mixture. I will discussing that in the later part. So after that, this ternary that diagram will be changed, and this addition of the benzene can help us to get the 100% anhydrous ethanol. There will be no presence of the water. So major engineering problem associated with that collection and storage of the molasses. There might be a special case. There might be some chances of contamination. So we need to take care of this thing. Maintenance of the sterile and specific yeast culture condition. You can see the only in this process only the fermentation tank is the batch process, whereas the other continuous distillations are occurring. These are all continuous process. So batch versus continuous operation, continuous molasses dilation in the end of the process and continuous distillations are incorporated to save space and equipment and operating costs. So the waste disposal, if it is uneconomic to concentrate for the cattle feed, must be used trickling method activated with large or anaerobic digestion to lower the BOD, biological oxygen demand, of that waste liquid waste before discharging to water run. Fuel economy in the series of the distillations that we are using, use of the preheat exchanger. Okay. Development of the methods to produce anhydrous alcohol from the 95% alcohol, which produces the azeotrope or constant boiling mixture. So we will discuss. This is the case of from the starch we are producing. Now the raw material is corn. Okay, so from the corn or from the starch we are producing the ethanol. Almost the same process. The initial few steps are quite bit different. First, the dehulled and ground corns are added. Water is also added. Recycled slopes are added in the continuous cooker. Cooker, the pressure is important. Pressure is maintained at 60 to 100 kilopascal gauge pressure. Okay, so this continuous cooker also we are providing steam. So in this continuous cooking process, whatever corn grains we are putting it as a raw material, these are pre-cooked for approx 1 to 5 minutes with the presence of steam and water, and temperature is maintained around 175 degrees Celsius. So cooking is essential to gelatinize the mixture so that barley malt amylase can convert the starch to fermentable sugars. So after the continuous cooker, where the main temperature was maintained at 175 degrees Celsius, these are passed through the flash chamber. There will be sudden temperature drop due to the flash. Temperature dropped around 60 degrees Celsius, Then it is passed through the mixture. From in the mixture there is addition of the malt and also addition of the mix like nutrient mixture, and also 1 to 2% there will be nutrient addition will be there. 1 to 2% alcohol mixed recycled water is also used here. Okay. Now after that, still the temperature is 60 degrees Celsius, but we cannot directly put to the fermenter because fermenter temperature should be maintained 20 to 30 degrees Celsius. So it should pass through the cooling pipes. So in the cooling pipes, the temperature is always try to maintain less than 35 degrees Celsius. So in the fermenter, we have seen that we are the same process. We have to introduce the yeast cell. Also, the temperature should be maintained in the fermenter. So, above the like at the upward section of the fermenter, we will be getting CO2 as a byproduct that should pass through the uh, scrubber so that CO2 can be separated. And from the bottom product, there will be beer. Beer it has 6.5 to 6.5 to 11% volume of alcohol is maintained. Okay, and this mixture is fed to the also pass through the preheat exchanger fed to the beer still. So from the beer still at the above mixture we are getting aldehydes and it is concentrated. Again the mixture is concentrated 50 to 60% and then it is going to the purifying column. Aldehyde will be separated from here. The same thing, the fusel oil separated and ultimately we are getting the alcohol, 90% alcohol. Okay. 90 to 95% alcohol. The same process is maintained. Now, what is the constant boiling mixture? You can see that this is the percentage alcohol by weight, and this is the temperature. This is the equilibrium curves. So this is the for the vapor composition equilibrium curve. This is the liquid composition. So as the temperature increases, increases, okay, temperature is this. Okay. As the temperature decreases, there will be a gap in the, see this much gap is bigger. So uh, this is actually TXY diagram. So temperature decreases and it reaches at a point where the two vapor and liquid composition they intersect. And at this maintain, and for that we are getting a constant boiling temperature where x equals to y occurs. It's around 78.3 degrees Celsius. This is the constant boiling mixture. Okay. Here we get around 95.6% of ethanol. 95.6% ethanol production is there. So this mixture is called as a constant boiling mixture. X equal to y occurs. So there is no further process of there is not possibility of separating the ethanol and water mixture further. So we need to incorporate a third component to disturb the system. That's what we will be discussing. .6% ethanol. At this point, LB is equals to composition same. So now we will focus on the absolute alcohol production, that is 100% pure ethanol production. So we need to do the something so that it will disturb the constant boiling mixture system. We will add a third component, that is benzene. Okay. So alcohol cannot be made stronger more than 95.6% by simple rectification method that I have discussed, because water forms binary constant boiling mixture of this composition which boils slightly lower than the absolute alcohol. Industrial alcohol, they have 95 to 96% alcohol, whereas there will be 4 to 5% presence of water. Formerly, this water was removed by absorption by using quicklime followed by distillation to get anhydrous method, but this process produces very high quality of anhydrous alcohol. It has surpassed as a very expensive process. We cannot follow that process. This is a good process that you pass through the quicklime solution, and it will be all the water will be getting out of the system, and we will getting anhydrous alcohol, but this is very expensive process. So for the alternative of this, ethanol and water form, we were finding any other solution. So ethanol and water, they find the forms azeotrope, which is the 95% volume of alcohol. Various methods are used, suggested for removing this last 5% water to produce the 100% pure alcohol. Oldest method is the distillation of the 95% azeotrope using the adding the third component, that is the benzene. This method forms a minimum constant boiling mixture, that is like it reduces the boiling mixture, that is the 64.85 degrees Celsius. It reduces from, it was earlier it was 78.15. Now it is reduced to 64.85. Now this temperature is lower than the water alcohol azeotrope, so we can simply evaporate the water from the system. Now the C6H6, which is benzene, which is the third component adding, following the phases are formed as shown in the figure. Next slide. Now there will be three binary minimum constant boiling mixture, two homogeneous mixture, one heterogeneous mixture, and one will be ternary. Ternary. Okay. So this is the ternary diagram. One end is for ethyl alcohol, this is for water, this is for pure benzene. Okay. So here, this is the three binary mixture in the system using benzene as a third component. Okay. So in the ternary mixture, the ternary mixture is the lowest boiling composition in the system, boiling at 64.85 degrees Celsius, which is pointing at a F point. Okay, lowest. The starting composition of the mixture must lie to the line CF. Ethyl alcohol concentration must lie to the line CF. CF. If the starting mixture is made by adding benzene to the 95% alcohol, the starting composition must lie along the line EB. E EB. If it is starting composition like benzene, it is having benzene plus 95% alcohol, then must lie on EB. The intersection G, it represents, at that condition it represents the starting composition G. If enough benzene is added to the 95% alcohol to bring the total composition to point G, the continuous distillation gives ternary constant boiling mixture at the top of the column and absolute alcohol at the bottom of the column. So this, when it is achieved, then we will have separation. See, this is the thing. So here we are doing the dehydration of the 96% ethanol. The 100% alcohol ethanol concentration by azeotropic distillation process. That is fed to the system. Azeotropic distillation occurs in the above. There is, we are getting the constant boiling mixture. That is sent to the heat exchanger and then to the separator. From the separator at 20 degrees Celsius there will be separation and the pure benzene reflux will be going back and benzene makeup will be there. From the bottom it is again passed to the next distillation column. At the top we are getting ternary azeotrope again. And at the bottom we are getting the benzene free aqueous solution. That is passed again to the distillation column and we are getting water where it is purified up to 96%. So here we are getting as a bottom product of absolute alcohol. These ternary azeotropes are further recycled back to the first azeotrope distillation process. We will quickly go through other productions by fermentation process. Citric acid, this is, you can see the structure. Citric acid C6H8O7. This is chain or branched kind of structure. Properties of the citric acid, this is a very weak organic acid. Its molecular weight is 192.124 grams per mole. Its density 1.665 grams per centimeter cube. Its boiling point T10 degree Celsius. Its melting point 153 degrees Celsius. At room temperature, it is crystalline. The form. So these are some basic properties of the citric acid. So this is you can see this is a branched chain structure. It is produced from sugar and dextrose. Those are simply a straight chain compound, but the production of citric acid, it is the branched chain structure. How the citric acid is produced by chemical reactions. The overall chemical reactions is, suppose sucrose you are having C12H22O11, you are putting water and aeration condition, we will get citric acid, sucrose, citric acid plus water, and if there is some inversion of sugar occurs, C12H22O6. So there will be some reactions, side reactions that also produce citric acid and water. Okay, this is side reaction. This is the main reaction. Submerged aerobic fermentation process. Here, the glucose dextrose syrup is raw material. It passes through the rotary filter, vacuum filter to remove the unwanted presence of impurity. Obviously, it should be diluted at first, and then the waste is discarded. The product is again diluted and sent to the contamination cell for more and then it is passed through the cooler to maintain the temperature, and then it is fed to the fermenter. In the fermenter also, yes, this is exothermic reaction, so water circulation is very important. This is the aerobic condition. Here is also spurger, through the spurger here is bubble up, and as a product there will be citric acid from the product, and the citric acid mixture is sent to the rotary vacuum filter unwanted impurities should be removed, and then there will be a liming tank. Lime slide is being used, and from the lime slide there will be some precipitate of lime, where what precipitate with the addition of the lime that should be further purified by rotary vacuum filter. And then again it is purified with H2SO4, de decomposing of the citrate, some calcium phosphate calcium sulfate and citric acid mixtures are producing calcium sulfate because we are increasing sulfuric acid, so it is passed through the rotary filters, and this is again decomposed liquor is being purified, and then it is passed through a lot of fixed bed and cation anion exchangers. It is further purified and then sent to the double or triple effect evaporator. In the evaporator, these are concentration is being improved, and then it is sent to the crystallizer to make it crystal form. In the vacuum crystallizer, there is crystal form, and then it is centrifuged to purify, remelt, and then again it is vacuum crystallizer, centrifuged to make the purity, and then it is drying, and then crushing or size classification is done for product specification and applications. So this is the overall citric acid, very simple. So next is quickly I will, there is no much time is left. So I will quickly go through the penicillin. Penicillin is a group of antibiotics that is derived from the mold Penicillium. It has been a modern medicines reversing the treatment of the bacterial infection. It is a beta-lactam thiazolidine. The core structure of the penicillin is beta-lactam ring, a four-member cyclic amide. The ring is crucial for the antibiotic activity. It interferes with the synthesis of the bacterial cell bus and leading to the cell lysis and death. Okay. So penicillin, it looks like this structure, RCONH kind of structure. So there you can see this R and this M, where the variation is R and M are possible. There are various types of penicillin. This M changes in the main ring. It will, if M is sodium, calcium, or potassium like that, so it will be changing on the change solubility of the product, and also the ingestion rate. M can vary, right? So that was the common formula for penicillin. So let's quickly go through the flow diagram. Fermentation medium is there, fermentation medium molds are added, air ventilation is done, temperature is maintained, and then there will be the product from the fermenter will be getting through the rotary filter press. There will be addition of H3PO4, that is a phosphate. Phosphoric acid is 10% is added. Then it is passed through the extraction.
extracted media. There will be buffer solution also. So the stripper will be there, and then the extractor is the purification process. So let's discuss with the process description. So an aerobic batch fermentation is carried out where the maize stick liquor or some it will be diluted to 4 to 5% solid. Okay, fortified with 4 to 5% lactose solid and nutrients such as magnesium, zinc sulfide all are there. CaCO3 is added to maintain the pH of the system. 5 to 6 various types of nutrients are also added. Organic precursor chemicals are also added to control the type of the yield of the penicillin. Type 2 penicillin requires phenyl acetic acid as a precaution. Now the batch fermentation process, this medium is sterilized with the steam at 115 degrees Celsius for 30 minutes and cooled with the water to 25 for maintaining the temperature, inoculated for a specific mold culture, and sterilized air is blown through the tank for 4 to 5 days under the temperature control. Penicillin is maximum for periodic assay extraction and separation of the penicillin from the fermented broth is accompanied by the solvent. Separation of penicillin from the fermented bud is accompanied by the solvent, and there will be continuous filtration and to 1 to 2 degrees Celsius. Clear filtered where the beer is adjusted pH of 2.5 with diluted phosphoric acid. Penicillin salt is extracted with amyl acetate, raffinate or water-phase is sent to the solvent recovery still. Extract is buffered with the sodium phosphate salt, pH maintained in the continuous mixture and crude penicillin returns to the aqueous phase. Mixture is centrifuged and solvent is recirculated. Penicillin is purified by second acidic extraction followed by reversion to a pyrogen-free distilled water solution containing alkyl salt of the desired element. Now the desired elements include sodium, potassium, calcium, aluminium, so their salts are used. Now the purified, because of the desired penicillin formation, purified aqueous concentrate is separated from the solution using a super centrifuge and then pressurized through a biological filter to remove the final traces of the bacteria and pyrogen. Then the solution is concentrated by freezing the freeze drying and vacuum spray drying. Crystalline penicillin salts can be obtained by salting out a standard saturated solution with a neutral salt containing the cations desired for the final penicillin salt. It can be further purified by recrystallizing from the organic solvents. Oil soluble penicillin is made by reacting a penicillin concentrate 20 to 30 with 50% aqueous solution. Now the procaine, a penicillin crystallizes from the mixture, so thus the penicillin is being extracted from the solvent. So that's all for today's lecture. The detailed of the penicillin and citric acid production by the fermentation process is already discussed in the NPTEL class. You can refer to those class. That's all for today's class, and we will meet in the next class next Friday 7 to 9 slot, and we will be discussing further other industry in details, following the basics and the flow typing. So thank you. I hope to see other students joining for the session for more interacting. Okay. Next session.